Welcome to Talk Tensors. Today we are looking at something that is fundamentally reshaping how we build artificial intelligence, even if it often gets buried deep in the infrastructure stack.
Sure.
We were talking about the long-term memory, the associative cortex, if you will, of modern AI. We are doing a deep dive into vector databases and embedding search.
Really is a massive architectural shift. I mean, we are effectively moving away from the era of keywords, what we call lexical search,
Right.
and into the era of meaning or semantic search. And, to be clear, this isn't just a software upgrade, it's a survival mechanism for data handling. If you look at the estimates, something like 80% of all digital data is expected to be unstructured.
Unstructured meaning the messy stuff. The stuff that doesn't fit in a neat little Excel sheet.
Exactly. We're talking about images, audio clips, video, and just mountains of messy, nuanced text. Your emails, Slack messages, research papers, traditional SQL databases, the ones that have powered the internet for 30 years, they just choke on this stuff.
You can't handle it.
They can't. They rely on exact matches. They can't understand that a picture of a canine and a picture of a dog are mathematically close. To them, it's just two completely different strings of data.
And that concept of closeness is really the heart of this deep dive, isn't it? We aren't just storing data in rows and columns anymore, we are mapping it. But before we get into the database wars, and there is definitely a war happening in the industry right now, we should probably unpack the mechanics. We keep hearing about embeddings. To someone new to this, that sounds incredibly abstract. What is actually happening, mathematically when we embed a document?
At its simplest level, an embedding is just a translation process. You take an entity, could be a paragraph, a JPEG, a bit of audio, and you run it through a deep learning model. The model analyzes all the features, and then it outputs a list of floating point numbers. This list is the vector.
Okay.
But the key insight here is that this isn't some random hash or an ID number. It is a specific coordinate in a high-dimensional space.
Right, and when we say high dimensional, we aren't talking about like 3D chess. We are talking hundreds, sometimes thousands of dimensions.
Precisely. If you imagine a standard 2D map, you have latitude and longitude. 2 points are close if they are physically near each other. Now, stretch your brain a bit. Imagine a space with, say, 1,536 dimensions, like you might get from one of OpenAI's models.
Which is completely impossible for the human brain to visualize, but we can kind of grasp it conceptually.
Right. Think of it this way. Each of those dimensions represents some kind of learned feature. Maybe one axis represents tone, another represents color, another's historical context, maybe another for sentiment. So when you turn a document into a vector, you are plotting it in this hyper-complex space. And the magic, the real breakthrough, is that concepts with similar meanings end up clustered together.
So searching isn't matching the letters CAT to CAT. It's calculating the geometric distance between the query's coordinates and all the document coordinates.
Correct. It's just geometry. You're literally measuring the distance between points.
Yeah. But here is where the engineering challenge kicks in. And this is why we have a whole new industry of vector databases. If you have 1 billion vectors measuring the distance from your query to every single one of them, that seems like it would take forever.
That is the brute force approach, yeah. Technically, it's called exact nearest neighbor search. And you're right, it just doesn't scale. If you are running a recommendation engine or a RAG pipeline for an LLM, you need milliseconds, not minutes.
You can't have the user waiting.
No, you can't do 1 billion math problems to answer one question. This is why the industry has shifted almost entirely to ANN, or approximate nearest neighbor search.
Approximate being the key word there. We are trading a tiny bit of accuracy for a whole lot of speed.
We trade a minuscule, often imperceptible amount of recall accuracy. Maybe you miss the 5th best result and get the 6th best instead for a massive, massive gain in latency. And the algorithm that basically runs the world right now, the one that keeps popping up everywhere, is HNSW.
Hierarchical Navigable Small World Graphs. That's a mouthful.
It is, but the logic is so elegant. HNSW is essentially a multi-layered graph. Think of it like a map application on your phone. When you are zoomed all the way out, seeing the whole country.
You only see the interstates and major cities. That's the top layer of the graph.
Right. You have very few connections, but they are long-range highways. You use that layer to get to the right general neighborhood of the data really fast. Then you zoom in to the next layer where the connections are denser, and finally to the bottom layer.
Which is like the street view where you find the specific house. I love that analogy.
Exactly. And it's based on that small world theory, right?
The 6 degrees of Kevin Bacon idea.
That's the one. In a small world network, you can get from any node to any other node in a surprisingly small number of hops. HNSW structures the data so that even in a data set of 1 billion items, the algorithm can just hop, skip, and jump to the nearest neighbor without looking at 99.9% of the data.
Okay, so we have the math, we have the vectors, we have the navigation system, but now we have this conflict breaking out in the industry about where this math should actually live. This is the great schism between dedicated vector databases and the integrated approach. On one side, you have people saying, look, I already have a database, just let me put vectors in there.
It is a classic consolidation versus specialization debate. The integrated camp has a very strong argument, often summarized as, Lucene is all you need.
And the scene powers Elasticsearch, right?
Elasticsearch, Solar. It's a giant in the search world. And they've implemented HNSW. The argument is logical. If you are already indexing text, why introduce a whole new piece of complex infrastructure just for vectors?
And we're seeing this with Postgres, too, with PG Vector. That has huge momentum.
It does. PG Vector lets you do vector operations directly inside a standard relational database. The benefit is massive for operations teams. You get ACID compliance.
Which is just database speak for your data is safe and won't get corrupted.
Exactly. You get simple backups, and you get database per tenant isolation for security, which is a big deal.
Right. If I'm a startup building some AI agent, using the Postgres instance I already have is incredibly appealing compared to managing a new complex system. It just simplifies the stack.
And honestly, the benchmarks show that for a lot of use cases, standard architectures using Lucene or PG Vector are good enough. They really are.
But then you have the specialized camp companies like Milvus, Qdrant, Chroma. They argue that vectors are a fundamentally different beast and treating them like just another data type is a big mistake. What's their argument for a whole new engine?
It comes down to extreme performance and cost optimization at scale. Dedicated vector databases are doing things that general purpose databases just struggle with.
Yeah.
For example, hardware acceleration. We're seeing systems co-designed with FPGAs, custom silicon chips, and heavy GPU used to just parallelize all those distance calculations. We are talking about maintaining sub-second latency on trillion vector data sets.
Trillion scale is just mind-boggling. But beyond just raw speed, I know some of these specialized engines are doing interesting things with compression because vectors are heavy.
Incredibly heavy. Storing 1,500 float numbers for every single paragraph of text, it eats RAM like you wouldn't believe. And RAM is expensive. So the specialized engines are pioneering techniques like binary quantization. They can compress these floating point vectors down to 1.5 bits or 2 bits per dimension.
Wait, back up. 1.5 bits. A standard float is 32 bits. That is a massive reduction. How do you not lose all the meaning? If I compress a picture that much, it just turns into noise.
It sounds like magic, but it works because of the unique geometry of high-dimensional space. You're compressing the data into these extremely compact binary representations that still preserve the most important directional information. And it works particularly well because of something called zero-value clusters that are common in modern embeddings.
Zero-value clusters?
Yeah, it turns out that in these massive vector spaces, there are large areas where the values just hover near zero. Specialized engines can exploit that statistical quirk to compress the data super aggressively. They basically decouple the query from the storage. You store the data in this highly compressed format to save 90% of your RAM.
But then you use a more precise calculation for the actual query.
Exactly. It's a level of optimization that is really, really hard to just bolt onto a legacy database like Postgres.
So the trade-off is clear. But there is a third architecture emerging that addresses the biggest pain point of all this: cost. Because vectors usually need to sit in RAM to be fast, you are paying for that memory every single second the server is on.
And if your app only gets used during business hours or has bursty traffic, you don't want to pay for a massive memory-optimized instance running 24/7. It's a waste.
This is the move towards serverless vector data management systems. There was a fascinating paper on a system called Vexless that proposed a really novel architecture to solve this. The problem with traditional serverless like AWS Lambda is the cold start. It takes time to boot up the function and load the index.
And that latency just kills the user experience. So what they do is use a global orchestrator. Instead of one giant index, they shard the data using an algorithm called constrained k-means clustering.
Okay, so they chop the data up into smart little buckets.
Exactly, buckets that fit perfectly into the memory limit of a small, cheap cloud function. But to fix the cold start, they use what they call stateful functions. The orchestrator predicts usage patterns and keeps certain functions warm. But here's the really clever part. They use volunteers.
Volunteers, like other users' functions.
Sort of. If a function is already running for one query and has some idle CPU cycles before it spins down, the orchestrator assigns it background tasks, like performing a more exhaustive search on a neighbor shard.
So it improves accuracy without costing an extra cent. That is brilliant. It turns the idle time you're already paying for into a performance boost. It shifts the model from paying for uptime to paying for actual computation.
Which is absolutely essential if we want vector search to be ubiquitous.
Let's pivot to why all of this matters so much. The why is driving billions of dollars in investment. The obvious killer app right now is RA, Retrieval Augmented Generation.
RA is the reason everyone knows what a vector database is today. Large language models have two, fatal flaws: hallucination and amnesia. They make things up, and their training data has a cutoff date.
So the vector database acts as the external brain.
Exactly. It's the updatable long-term memory. Before the LLM answers your question, it consults the vector DB, retrieves the relevant facts.
Like your company's latest policy document or breaking news.
Right. And then it generates the answer. It grounds the AI in reality.
But it's going beyond just text now. We are seeing the rise of multimodal pipelines. This is where I think the magic factor really kicks in for people.
Absolutely. This is driven by models like CLIP for images or Whisper for audio. We can now map text, images, and audio into the same vector space. They're all translated into a shared language of meaning.
Give me a real-world example of what that looks like.
Imagine a security system. You can type a query, find video footage of a red truck backing up. The system converts that text into a vector. It then searches the vectors of the video frames stored in the database. It finds the visual match for the semantic concept of red truck and backing up, even if no human ever tagged that video with those words.
That is basically the Star Trek computer. You just talk to it and it finds the thing. But I have to play the cynic here. With great power comes great security risk. These vectors, they can leak data, can't they?
They absolutely can. There are attacks, model inversion attacks, where you can sometimes reverse engineer the original text or image from the embedding. If you embed a medical record, that vector is sensitive data.
So we can't just treat them like harmless hashes.
No, this is creating a huge demand for what we call attribute filtering. You have to enforce permissions during the vector search, not after. You can't just find the top 10 results and then check if the user's allowed to see them.
Because maybe the user can't see the top 5 and now your search returns nothing useful.
Exactly. Your results are irrelevant. You need to filter the graph traversal itself inside that HNSW structure to ensure tenant isolation.
Which adds another layer of complexity. Now you're looking for the nearest neighbor that I'm allowed to see.
Correct. And doing that without destroying the performance is a major area of active research right now. It's a very difficult problem.
All right, that brings us to the part of the show where we take the safety rails off. It's time for novel notions.
And the standard disclaimer. The following segment is for entertainment purposes only. These are just speculative ideas based on the technology's trajectory.
I'll kick us off. I've been thinking about this serverless trend and the crazy quantization down to 1.5 bits. We're getting to a point where vectors are cheap and almost instant to generate. So my notion is the ephemeral context cloud, or, the throwaway brain.
The throwaway brain. Okay, I'm listening.
Right now, we treat vector databases as these persistent libraries. We cherish every vector, but human memory isn't like that. We have short-term memory that gets flushed. I imagine a future where your personal AI, your phone, whatever, spawns a temporary microvector database for every single day.
So it's indexing the conversation we're having right now, the article you just read, all of it.
In real time into a disposable cloud instance. But here is the kicker. The orchestrator manages time. If a memory vector isn't reinforced, if you don't query it again, the database just dissolves it after 24 hours. It mimics biological memory consolidation.
That's fascinating. It also kind of solves the privacy issue. You aren't building a permanent surveillance log of your life.
Exactly. The default state is dilution, not retention. You have forgetting as a feature.
Okay, I like that. My notion takes that idea of a self-healing system and pushes it to the extreme. I call it generative indexing.
Generative indexing. What's generating what?
Right now, the index is passive. But imagine an LLM that lives inside the HNSW index structure itself. It watches every query that comes in.
Like a librarian watching over your shoulder.
Exactly. And if a user asks a question and doesn't click on the top result, if the search basically fails, the internal LLM analyzes why. It sees the gap between what was retrieved and what was wanted.
Okay, so it sees the failure, and then what?
Then, and this is the radical part, it actively rewrites the vector values of the stored items. It physically moved the document that should have been found closer to the query in mathematical space.
Whoa. The database is changing its own data.
Effectively, yes. It performs gradient descent on its own storage structure without any human intervention. The database learns from failed searches, evolving its own small world shortcuts to better match how its users think.
That is wild. The database isn't just a bucket anymore. It's an organism that evolves to become more searchable over time.
It would be a database that optimizes itself based on confusion.
I love it. The self-optimizing graph. Well, whether our databases start thinking for themselves or we just keep cramming them into Postgres, one thing is clear. The ability to recall information by meaning rather than keyword is the defining feature of this decade of computing.
It really is. It's the difference between a filing cabinet and a librarian.
Thanks for listening to Talk Tensors.